The 2006 census shows that the number of males living in Ireland is about the same as the number of females. If a person is selected at random, write down the probability that the person is male. So this circle represents the population, and it consists of roughly equal numbers of males and females. To make the calculation easy, we'll say that the number of males is equal to the number of females. A person is selected at random from this population. What does that mean? Well, it just means that each person has the same probability of being selected as everyone else. So the probability of selecting, say, this particular person is equal to the probability of selecting this person, which in turn is equal to the probability of selecting this person, and so on. Everybody has the same chance of being selected. As a matter of fact, the probability of selecting one particular person, it might be a person you happen to know, would be 1 over the total number of people in the population. The letter capital N is often used to represent the size of a population. Suppose that the number of people living in Ireland in 2006 was 4 million. Then the probability of selecting a particular person from this population would be 1 divided by 4 million. To find the probability that that person was male, we just put the number of males over the total number of people. Well, since the number of males is roughly half the total population, the number of males will be 2 million. So we put 2 million over 4 million, and when we work that out, we get a half. Another way to think of it is to realize that since the number of males is equal to the number of females, and if we make a random selection, we select a person from the population at random, well, the chances that we will select a female will be equal to the chances that we select a male. In other words, the probability of selecting a male, which I'm writing P of M, equals the probability of selecting a female. Now, another thing to realize is that the probability of selecting a male plus the probability of selecting a female must equal 1. Why is that? It's because there are only 2 outcomes for a selection. Either we select a male or we select a female. 2 and only 2 outcomes. That means that the probabilities associated with those 2 outcomes must sum to 1. So P of M plus P of F must equal 1. Now, since P of M is equal to P of F, it means that P of M must be a half and P of F must also be a half. These must be equal and they must add to 1. So you can see the answer is a half. Now, I spent a long time laboring this problem. I just wanted to clear up some ideas about probability that might be useful in more difficult questions. 4 people are chosen at random. We are interested in whether they are male or female. Complete the sample space below showing the 16 equally likely outcomes. Now you've got to imagine a situation where we are sampling one person at a time with replacement from the population. So if we want to take a sample of 4 people, what do we do? Well, we look at the population, we randomly select a person. That means each person has the same chance of being selected, just like in part A. So we randomly make a selection. Let's suppose that the selection we make is a male person. Happens to be male. We know the probability of that happening is a half. So we note down the gender of that person. So we have a male person. Then we put that person back into the population. So we replace this person. And now we make another selection. So we make another random selection. And let's suppose that person is a male person. That probability is a half again. Then we put that person back. So every time we make a selection, we're selecting from the entire population. So the probability is a half. Let's suppose the third selection happens to be male. Then we put that person back in again. Then we make a 4th selection. That person happens to be male. Then we put the person back again. So we have this sample. This sample consists of 4 males. If we want to find the probability of selecting 4 males, we just take the probability of selecting a male, which is a half, and multiply those probabilities together. So we get a much smaller probability of 1 over 16, which makes sense. These are independent events. Each time I select a male, that's a probability of a half. So we expect a much smaller probability of selecting 4 males, because we could have more likely selected some females in our later selections. It's just like throwing a coin. It's just like the probability of getting 4 heads. If you throw a coin, it's a half times a half times a half times a half, which is 1 over 16. It's quite unlikely. Now let's consider the situation where our sample of size 4 consists of 3 males and 1 female. So let's suppose now we make a selection from the entire population and we get a male. Then we put this male back again, sampling with replacement. Then we make another selection. We happen to get a male person. We put that person back in again after noting down the gender. So the first 2 selections were male. Then we make a third selection and it's a male person. We replace that person. Then we make a 4th selection. The 4th selection happens to be female, and then we replace that person. So we note down the gender of each person in our sample. So we have a sample of size 4 that consists of 3 males and 1 female. The first 3 selections happen to be male. The 4th selection happened to be female. Now this is not the only possibility for a sample of size 4 which consists of 3 males and 1 female. We could have had this situation. This sample consists of 3 males and 1 female. So we have to allow that there are different ways to get a sample of size 4 which consists of 3 males and 1 female. So we have to consider all the different ways such a sample can arise. Here is another way that we can select a sample of size 4 consisting of 3 males and 1 female. The second person selected could have been female. So I've listed it here. Is there any other way this can happen? Well, the first person selected could have been female, and the other 3 males. And that's it if you think about it. So we just have to arrange the letter F amongst the 3 letter M's. Now suppose that in our sample of size 4 there happen to be 2 males and 2 females. So I have one such possibility here. The first 2 are male and the second 2 are female. So how many ways can we get a sample of size 4 consisting of 2 males and 2 females? Well, how many ways can you arrange the 2 letters, the 2 M's and the 2 F's amongst themselves? We have F, F, M, M. There is another way actually. M, F, F, M. The 2 females are in the middle. So we can have the 2 females at the start, 2 females at the end, 2 females together in the middle. We can also have them separated like this, MF, MF. Actually, there's another way to separate them, FM, FM. And they're separated here as well, FM, MF. We could actually calculate the number of ways of arranging 2 males and 2 females. First of all, consider the number of ways of arranging 4 distinct objects. Now these are distinct, that's why I'm calling it M1 and M2 to distinguish these 2 M's, and F1 and F2 to distinguish the 2 F's. So we have 4 distinct objects here. We know from the fundamental principle of counting, which is covered in the previous video, that we have 4 ways to select the first object, to place the first object at the start, 3 for the second, 2 for the third, and just 1 way for the fourth. By the fundamental principle of counting, we multiply these together, 4 by 3 by 2 by 1. Shorthand notation for that is 4 factorial. So that was covered in the previous video. But notice there are 2 factorial ways of arranging 2 objects, of course. And let's take the 2 F's, F1 and F2, and we have 2 factorial ways also of arranging M1 and M2. So the way we would actually get the number of ways of arranging M, M, F and F would be to take 4 factorial and divide it out by the number of ways of arranging the two objects that are the same. So the two f's are the same and these are the same. So now we pretend that they're the same. And we divide the 4 factorial by the 2 factorial ways of arranging the two f's, which are the same, and we also divide it by the 2 factorial ways of arranging the two m's. So this is the answer to the number of ways of arranging m, f, and f, where the two m's are the same and the two f's are the same. So if we interchange the two m's, it doesn't matter, and if we interchange the two f's, it doesn't matter. We have the same arrangement. So we need to divide it down, because for each of these 4 factorial ways of arranging 4 distinct objects, there are 2 factorial ways of two ways that we can move the f's amongst themselves. We could replace f1 and f2 for each of these, and we can also replace the two m's or interchange the two m's for each of these 4 factorial ways. So we need to divide out by those. And if we calculate this, what do we get? Well, 4 factorial is 4 by 3 by 2 by 1. That's 24. 2 factorial is just 2. 2 by 1 is 2. And the other 2 factorial here. So we have 24 divided by 2 times 2. 24 divided by 4 is 6. So there should be 6 ways of, or 6 samples size 4 that consists of 2 males and 2 females. 6 different ways that we can have 2 males and 2 females in a sample of size 4. So you see we have all 6 of them here. Well, you don't have to worry about the calculation. You know, it's not too difficult to figure them out just by writing them down. Okay, let's consider the situation of a sample that consists of 3 females and 1 male. Here is one possibility for a sample of 3 females and 1 male. The first person selected is female, the second is female, the third is female, and the fourth is male. So how are we going to get all the different ways? Well, all we have to do is look at all the ways, or all the different samples that consist of 3 males and 1 female. That number of ways is going to be the same as for the number of ways, or number of samples consisting of 3 females and 1 male by symmetry, because the probability of selecting a female is equal to the probability of selecting a male. So we have that symmetry. So we only have to refer to the 3 males and 1 female situation. So we should get 4 of them, like we got there. So we can arrange the male amongst these letter F's. So we have F, F, M, F. We have F, M, F, F. And then we have the M followed by 3 F's. So we have 4 of them all together, just like we had here, 1, 2, 3, 4. Of course, we could also calculate it. The number of ways of arranging 4 distinct objects is 4 factorial, and we divide out by the number of objects that are the same. Well, or the number of times a particular object is repeated. The number of times that f is repeated is 3 times, so we would be dividing by 3 factorial. And it's only the letter f that's repeated, the letter m is not repeated. So the 3 factorial represents the letter f that's repeated 3 times. And if we calculate this, we get 4 factorial is 4 by 3 by 2 by 1. 3 factorial is 3 by 2 by 1. So you can see that these we get 4 for our answer, so there's 4 ways. Now there is one outcome left, and that outcome is the outcome that consists of 4 females. So you can see that there are 16 outcomes altogether. They're equally likely, actually. As a matter of fact, we could work out the total number of outcomes. We could work out that there must be 16 outcomes, because there are 2 ways to select the first person. The first person selected could either be male or female. Then that person is replaced back into the population. And there are 2 ways to select the second person. The second person could be male or female. There are 2 ways, or 2 options for the third selection. That person could be male or female. And finally, there are 2 options for the fourth person. So the total number of options, by the fundamental principle of counting, is got by multiplying these numbers together. And you see that this is just 2 to the power of 4, which is 16. Now, by the way, each of these outcomes are equally likely. The probability for the 4M's, as I showed you earlier, probability of getting 4 males was a half times a half times a half times a half, because we have 4 independent events. We're sampling with replacement, so each event is independent. So when we have independent events, the probabilities are multiplied together to get a much smaller probability, 1/16. And it doesn't matter whether it's 4 M's or say 1M, MF, MF. This is also a half times a half times a half times a half. The probability of selecting a male is a half. The probability of selecting a female is also a half. So we're going to get 1/16. For each of these, the probability is 1/16. And of course, all 16 of those probabilities add up to 1. We've 16 sixteenths, which is 1. So what's the probability of getting 3 males and 1 female? So we just count all the samples that consist of 3 males and 1 female. There's actually 1, 2, 3, 4 of them. I could do this in red as well, actually. 4 males, 1 female. And we put that number over 16. The probability of selecting one of these 4 out of 16 is 4 over 16, because there's 4 of them. So there's 4 samples that consist of 3 males and 1 female, and we put that number over the total number of outcomes. So here are the probabilities. We just count up the number in each category, the number. So there are 4 ways we can have 2 males and 2 females. These are the ones in. I'm sorry, this is 6. And there are 4 consisting of 1 male and 3 females, and just one sample that consists of 4 females. Now to check these should all add up to 1, of course. You see, we have 1 plus 4 is 5, plus 6 is 11, plus 4 is 15, plus 1 is 16. So we've 16 over 16, which is 1. Because we've covered all the options here. If we have all the options covered, then the probabilities associated with all the options must sum to 1. A person states the following: if you pick 4 people at random, it's more likely than not that you will get 2 males and 2 females. Is this statement correct? Well, what is the probability of getting a sample that consists of 2 males and 2 females? Well, how many samples consist of 2 males and 2 females? 6 of them. That's 6 out of 16 possibilities. 6 over 16. Now, more likely than not means that we want to see if this probability is greater than a half. If it's greater than a half, then it's more likely that we will get 2 males and 2 females than not get a sample consisting of 2 males and 2 females. Well, this is not true, actually. 6 over 16 is less than a half, because a half is 8 over 16, and 6 over 16 is less than 8 over 16. So you could say we are less likely than not to get 2 males and 2 females in our sample of size 4.